So hello, my name is Susan Kassin. I'm a NASA postdoctoral program fellow at NASA's Goddard Space Flight Center. Today I'll be talking to you today about the epoch of disk settling from redshift 1 to today. I'm an observer, I measure kinematics, but I'm showing you a simulation from Fabio Governato, which is very similar to the ones that many of you are probably running. And it shows the formation of a Milky Way-like system. And what it shows is a galaxy forming out of disorder and then settling down to be like galaxies today. As you'll see, it evolves over time from a lot of minor mergers, a lot of smooth accretion, to more or less an ordered system. I'm not going to play the whole thing, but you get the point. So what do these simulations tell us about galaxy formation? As an observer, I say, well, most of the mass and angular momentum of galaxies may come from these cold flows, and then there's more merging accretion at earlier times. So at a redshift about 1, this is what we know about galaxies. This is what an observer knows. There's many pieces of evidence that the blue galaxy population is not changing very much at all. First of all, we know that galaxies are brighter by only about a magnitude at redshift 1. Their number density doesn't change since redshift 1. Their stellar mass is unchanging to its uncertainties since redshift 1. And the sizes are smaller by only a factor of 1.5. So naively interpreting this information, I might say something like, oh, the Hubble sequence is in place. Galaxies are more or less very similar to those today. However, there are some key differences. One is that they have higher star formation rates by a factor of 10. It's huge. They have more disturbed morphologies, at least qualitatively. And they have higher molecular gas fractions. So something is up. So let's look to kinematics to try to find out what exactly is going on. Sample selection is key when you look at kinematics. If you select high redshift galaxies just like those today, you're going to minimize evolution. And many past kinematic samples have done that. It's a bit of a trap. So I'll just say our final sample is essentially selected on emission line strength and magnitude. And here it is. This is a color magnitude diagram that you're probably very much used to. Color, magnitude, in decreasing redshift bins from redshift around today to redshift at 1. And this is the blue cloud, and this is the red sequence. The black points are our base survey, the deep 2 survey, and the gray points are the deep 2 survey, the field 1 of that, and the black points are galaxies selected to measure kinematics from. As you see, we more or less trace the blue cloud. It's more or less a well-represented sample. Representative sample, excuse me. So most blue galaxies today play nice. They like to rotate in the XY plane, and then they move up and down a little in the Z-axis. The stars and the gas in the galaxy play nice. Most blue galaxies at redshift 1 play rough. They rotate and they show disordered motions. They're quite odd looking by eye. And perhaps this is like our Milky Way once was, as you'll see later in the talk. So what we do, we observe galaxies with slits to get spectra of them, and we measure kinematics from emission lines in the spectra. Locally, you put a little slit, very thin slit down a very nice well-ordered disk galaxy, you get a rotation curve. And you get a measure of the velocity dispersion. At high redshift, we also use thin slits, but galaxies are smaller. So what you measure, you're able to pick up a rotation velocity, but what you measure as the velocity dispersion is intrinsically different. You're measuring it from measuring a velocity dispersion from emission lines from the gas, so it's not collisionous. And what that ends up being is an integration of all the velocity gradients beneath the line of sight across the face of the galaxy. These are Hubble images. They're without seeing. If you add in seeing, you blur these galaxies out quite a bit. So you get, with the velocity dispersion, an average measure of the disordered motions of the system. These are 3 example galaxies. There they are again. This is rotation-dominated system, a system that has dispersion-dominated, and one that's mixed. And you can already see that the kinematics is well correlated with the morphology, the visual or the photometric morphology of the systems. So I'll go through this rather quickly since it's sort of old. This is the Stellarmass-Tully-Fisher relation, stellar mass versus rotation velocity in increasing redshift bins for galaxies in the deep 2 survey in the Aegis field. This cutoff here is simply due to survey selection. You can't see faint things at high redshift. And I color-coded galaxies here according to whether they look to me disturbed or compact or normal. If they were disturbed or compact, I plotted them as a red point. If they were normal, I plotted them as a black point. And what I want you to take away from this is there's tons of scatter in Tully Fisher once you open up your selection and don't select only the well-ordered systems that are on the local relations here. And this scatter is present to high redshift. And here is that same Tully Fisher relation in a given redshift bin, 0.65 to 0.925. And in this figure, I plot galaxies that are normal end on the Tully Fisher ridge line here on this side, galaxies that scatter off of that relation and that are odd on this side, just so you can get an impression of my just quick visual morphologies. So at redshift 1, you do have these more or less disk-like systems, and then you also have a nice bunch of galaxies that are odd. So let's incorporate this velocity dispersion into a kinematic quantity. And this kinematic quantity should trace the potential wells of the system since it's measuring the total kinetic energy of the systems. I'm not going to go too much into this, but here's the Tully Fisher relation that I just showed you, and when you use the S factor, you get a relation that's very tight, that doesn't revolve to within uncertainties, and that's coincident with Faber-Jackson. So let's move on from this, and let's look at a mass-complete sample, looking at all these galaxies here in gray. And let's look at the evolution of rotation velocity, of integrated velocity dispersion or disordered motions, and S.5 individually. There's a lot of scatter, it's the first thing you notice, but here is sigma versus redshift, rotation velocity versus redshift, and S.5 versus redshift. The points are the individual galaxies, the red triangles are median points. And the red lines are fits to the median points. And what you see is that the amount of disturbed motion simply decreases with time. The amount of rotation velocity increases with time monotonically, with redshift, I should say. And the S.5 factor increases slightly with time. So blue galaxies become more ordered and increase in potential well depth over the last 8 billion years. And I'm going to show you later on in the talk that some of this scatter is indeed due to stellar mass. But first, let's look at these ratios with respect to S.5. So here's the disordered motions over the potential well depth. Here's ordered motions, or rotation velocity over the potential well depth. And again, we see these similar trends. Decreasing disordered motions, increasing rotation velocity. Blue galaxies become more ordered and increase in potential well depth over the last 8 billion years. So this is something that we call kinematic downsizing. It's cute. Bring a term in from back 10 years ago. Here's sigma over S.5, and here I want you to focus on the median points up here, where I color-coded galaxies according to their stellar mass. The most massive systems here are in red. They're these red-filled points. The lower mass systems here are in black. They're these black open triangles, and the systems that have a mass in between are these gray triangles. Sorry, these are squares, the black open squares and the gray triangles. And what you see is that at any redshift, the higher mass galaxies have a lower sigma. Have a lower sigma over S.5 and have a higher V-rot over S.5. So they are the most well-ordered at all times. The lower mass galaxies at all redshifts have a higher amount of disordered motions and a lower amount of rotation velocity with respect to their potential well depths at all redshifts. And the intermediate mass galaxies are somewhat in between. So again, this is some sort of kinematic downsizing. So when is a disk galaxy settled? I chose to define that with V-rot over sigma. If V-rot over sigma, if I said is greater than 3, it's settled. And these are 3 examples of galaxies that I call settled. V-rot over sigma is less than 3, it's not settled. And these are 3 examples of galaxies that are not settled. So you can see that the kinematics is correlated with the visual morphology. And I chose this number 3, to actually be to really bifurcate what I thought was more oil-ordered systems from more disordered systems. And let's look at the fraction of settled disks of settled blue galaxies versus time or versus redshift for different mass bins. Here's the settled fraction. Here's redshift. And these are galaxies broken up into different stellar mass populations. The red is the most settled at all times, and they all increase. The green is the next settled. The blue is the next amount of settled, and then the lower mass, the black, is the least settled. So the settled fraction increases with time. The more massive a galaxy population is, the more settled it is at any redshift. And we find the same qualitative behavior for thresholds between 1 and 4. So what processes cause disk settling and formation? Mergers, minor and major, might rile up the disks. Mass accretion might also disturb the disks, many of you have found. And then we know that galaxies have likely had larger gas reservoirs in the past. This should cause more star formation and more feedback. And then, of course, there's the violent disk instabilities. So these processes, the processes responsible, they need to decline earlier in more massive systems. So this is why I'm here. I'm here to find out from you what is going on, because we need simulations to investigate that. So the conclusions are the following. Most disk galaxies are not in their final state at redshift 1. They have significant disturbed morphologies and disturbed motions. 2, galaxies increase in V rho and S and decrease in sigma with time. 3, the more massive a galaxy is, the more kinematically ordered it is at any time. We are essentially seeing the creation of the Hubble sequence for disk galaxies between redshift 1 and now. And it'd be nice to know what roles minor and major mergers play, feedback, and accretion, and how simulations and SAMs can be used to figure this out. And I will leave you, well, I have time, I spoke very quickly. Let's see. This is a very complicated plot, and I have time to speak about it. Sorry. This is rotation velocity versus redshift. This is sigma versus redshift. Galaxies here are taken from the literature and also from the talk I just showed you. What I just wanted to show you is our galaxies here, they're plotted in light gray points, and here's our fit, rotation velocity versus redshift. Here they're also plotted in light gray points. Here's the fit. And these are the median points. Galaxies are color-coded red if they're more massive, blue if they're less massive. What I want you to take away from this very complicated-looking plot is that here, up to redshift 1, we have the kinematics. We have a nice, well-defined sample of galaxies in which we're measuring a nice monotonic trend or progressive trend. And then at redshift 2, the situation is very different. It seems to be almost bimodal. You have these rotation-dominated systems, and then you have systems that are quite sigma-dominated, that are down here. I cheat a little bit. The open symbols here are galaxies where they were able to model a rotating disk, and then the filled symbols here are galaxies which they were unable to model as rotating disks, in which I adopted the velocity shear as the rotation velocity. So we still have a lot of work to do down in here to really get a complete sample, but that will come quite soon. So that's all I have. Thank you.